Hi, everybody. Happy day 149. Can you believe it? There's only 38 actual days of life left until the end of school. And then social distancing summer. Woo! Yeah. It's going to be lit. Fire. Make little flames come up. All right. So, for today, a light day. If you have questions about the Changing Pitch Lab, send me a message. If there's any information that you feel like you either couldn't figure out on your own, or or maybe you don't have the materials and you watched my demo video and there wasn't quite enough there for you. I think there was, but if there wasn't, let me know and I will make a new video that focuses on whatever you need and send it to everybody. So let me know. Remind message, Schoology message, email, whatever it takes. Okay. Those of you that are out there doing stuff and turn it in, I'm looking at it. Awesome. Thank you. Good job. Keep it up. Keep up the learning. Uh, okay. For today, this is a hands-on activity, and unless you have tuning forks at home, and unless you're a pretty serious musician, you probably don't. Um, but I have them here, and I will use the slow-mo camera on my phone to make a separate second video that I'll stick with this one and upload. Okay, so that'll be there a little bit after this. Let's go over your warm up and the classwork, which is pretty brief. So, main goals for today is that you're able to take some information and calculate time, right, using the wave equation, and calculate for today time, and then think about how far this actually is, and answer a question. Other goals is that you can observe differences in tuning forks and different lengths of material and how they vibrate differently, right? Like if you have something long versus something short, how they vibrate differently. So I'm going to do a few demonstrations with that to help you understand how the length of the vibrating thing affects its frequency and therefore the pitch that we hear. Okay, I bet you've actually done some of this before. Materials for today, like I said, if you have, it's a long shot. If you have tuning forks, great. If you don't, if you have a ruler, grab it. All right, grab it for today. A ruler or just a piece of wood that's thin but kind of long. That'll do the trick. Even a pencil might do it. All right, you've probably done this demonstration before that I'm going to show you. Okay, so go grab those things and then come back. Okay, ready? Here we go. I have a couple rulers for when we get to this. All right, let's go over the warm up. So, speed of sound 5,120 meters per second. That means that every second, sound waves are traveling 5 kilometers. That's about 3 miles in a second. That's really fast. This is for iron. And so we use this approximation because there's a lot of iron in the crust of the Earth. And so it's a decent approximation for how fast earthquake waves travel. So how long would it take for sound waves to get through this much solid iron? Excuse me. Well, definitely a while. How long? Hard to say. But this is a distance. This is a speed, and speed is distance divided by time. If we flip the place of speed and time, then we get the equation for time, and time is going to be our distance number divided by our speed. So we just need to take our distance, 40,075,000, and divide that by 5,120, and we get 7,827 seconds. And to put that into perspective, if we divide that by 60, that gets us 130 minutes. If we divide that by 60 again, we get about 2.17 hours. So that's 2 hours and blanking. 0.17 times 60. Okay, so 2 hours and about 10 minutes. So there you go. Does this ever actually happen? Could a sound wave travel that far? Well, if you looked up this number, you may have noticed this is actually a special number. This is the circumference of the Earth at the equator. So if you were to walk on the equator, fly over the equator, and go all the way around the globe, then that would be this far. This is 40 million meters, or 40,000 kilometers, or in miles, 40,000 or 75 divided by 0.6. No, sorry. 1.61. 24, almost 25,000 miles. Keep in mind, it's a little more than 3,000 miles from west to east coasts of the United States. So this is about 8 times that. All right, 8 times would be like driving across the country and back and doing that whole thing 4 times, 4 round trips. Right? Definitely would take a while. Okay, it takes 2 hours and change for that to happen. Could that happen? It actually has happened. Large earthquakes, the wave pulse makes it all the way around the Earth, and then it comes back to where it started a couple hours later. Definitely much weaker. You'd never feel it as a human. If you did, probably the world would be ended, and you would have died the first time. But hey, but a seismograph could feel it, right? So it happens. Okay. Again, any questions about the pitch lab, let me know. Okay, I gave you this pre-lab question. This is very similar to the one that we just did, except this time now you're trying to solve for wavelength. And so if we want to know the wavelength, let's see. Is that here? Here we go. So our wavelength equation. While we're doing this, let's pause. Thank you, Derek. Drinking my last Japanese Coke. Very delicious. Okay, we want to find wavelength. Let's see, any of these equations that are actually solved for wavelength. We got 3 here. Which of these would be best to solve for wavelength if we have... What do we have? What are our givens? We've got a velocity or a speed. We've got this thing. What's this? It's a frequency. Okay. So we have a speed and a frequency, and we want to know wavelength. So wavelength is in 2 of these. Which one also has speed? Okay, both have speed. Which one has frequency? Not that one, this one. So we're going to use this guy. And we want to solve for wavelength. So that means it's going to be wavelength equals velocity or speed divided by frequency. Okay, so we need to divide the speed by the frequency. So let's do that. Here we go. So the speed was 343 meters per second. The frequency is 500 hertz. Hertz is 1 wave over, it's cycles per second or waves per second. So this would be 500 waves per second. So 343 divided by 500. There we go, 0.686 to 1 sig fig, because that's all we get. It'd be 0.7. But the wavelength would be 0.7 meters. So 0.7 meters would be, on me, there we go. So from the center of my chest to my fingertips, way over here, is a meter. And so 0.7 meters would be about from my shoulder to my fingertips. So that's how long one wave is going to be. One wave, again, being up, down, and then back to the equilibrium point. All right, that S, that's basically laying down like this. Oh, it's hard to get your arm to do that. Okay, so for our activity today, you need 2 tuning forks, 1 high and 1 low. So here we go. Tuning forks. Obviously, you can see there's some differences with these. So here they are. And you need to write down the frequencies. So I don't know if you can see these. I tried watching one of my videos the other day, and the, what do you call it? Resolution wasn't that great. This one's 261.6 hertz. This one is 880 hertz. There you go. You can probably see it now. And you can definitely see that these are very different lengths. They're made of aluminum. They got a handle, and these pieces are flexible. See that? I can squeeze it. It moves. This one too. This one's a little bit harder though, because it's a lot shorter. You gotta be really buff to do that, by the way. Just saying. Hope you guys been working out over the quarantine. Fit. Yeah. All right. So what you're going to do and what I'm going to do, and I'm actually going to do this now, but then I'm going to do it again with my phone because I have a slow-mo, high-res camera, and I'm going to upload that. So we're going to bang this and listen to it and make some observations. When you use these, you don't want to hit them on something really hard. You want to hit them on a stack of paper or something like that, something that's going to get them to vibrate but not damage the metal. So I've got a little stack of paper here, and great. There's my closet. It's my wife's fault. And here we go. Start with this one. You can probably see that these look blurry. That's because they're vibrating. I'm gonna stop them. See? Okay, let me do the 880 hertz one. Probably don't look very blurry. They're not vibrating very far. Can you hear the change? Hopefully this sounds different as I rotate it. These are actually directional. The waves, remember how we looked at the two tennis balls bouncing, there being interference patterns. Well, there's two things here, and they're bouncing. They're not bouncing into liquid water, they're bouncing into another fluid, air, and sometimes they constructively interfere to make a loud sound, and if you rotate it a bit, they destructively interfere to make a quiet sound. And so hopefully you were able to hear as I rotated this. Oops, got barbecue sauce on it. All right, but this is for lunch. Yeah, they constructively and destructively interfere depending on the position. Okay, so we've got the frequencies. We listened to the sounds and compared them. You should make a data table is a great way to organize your information for these. Okay, so next is to strike the tuning fork and have it touch your ear and nose. So we're gonna do that next. Okay, I got my volunteer. This is my coworker, Jackson. What? What are you doing? Child abuse. Wait. All right. I got my helpers. Say hi, Luna.
Hi.
Say hi, Jackson.
I don't want to do it.
I know you don't.
Hi.
All right, here we go. Just gonna touch your ear. Here, help me hold it. Got it? Oh, we'll do your nose first. How did it feel? Don't move. Don't move. Don't move. Don't move.
But you already did my nose.
Okay, let's touch your ear. How did it feel when it touched your nose?
It hurted.
No. Okay, let's touch your ear. Don't move. Don't move. Don't move. Don't move. You can't touch it.
You.
How did it feel?
Can you do
Oh,
my little one? Can you do the little one?
Yeah, you want to try it?
I guess this is not. No, the little one.
You want to try the little one? All right, we'll try the little one. Touch it to your ear.
What are you guys doing?
How's it feel? Here, Jalen, you want to come be brave since these guys are lunatics? We're feeling how this feels on your ear. Here, touch that to your ear.
That was weird.
Accurate high school student response. Thank you. How did it
Can
feel?
you do my nose? Can you do it
It's
my
not
nose?
interesting. Yeah, I can do your nose.
I want the little
No, you gotta do
one.
the big one. The big one's better. Trust me. Do it again. That was funny.
What grade do you teach?
I'll do it. I'll do it.
You teach in high school.
Ah.
What grade do you teach?
Teach freshmen and some sophomores, juniors, and seniors.
Mostly freshmen.
Mostly freshmen. Yeah. Where'd you go? All right, good stuff.
That we need to do.
What's next? That's it. Thanks, guys.
Mom, if we bang the put in your nose, I'm gonna do it to
Did we
you.
see our dirty run?
I'm gonna do it to you. I'm gonna do it to you. I'm gonna do it to Daddy.
Okay, you can do the little one. Bang it, Jackson. Touch my ear. Oh. All right, Lily's gonna do the little one. You gotta bang it harder, like that. Touch it. Ooh, it tickles. Thanks, guys. Okay, next we're gonna strike the tuning fork and we're gonna touch it to some water.
Wait, Daddy.
So let's see.
Do not do it yet.
I'm doing it right now. Let's see what happens. All right, here we go. Let's see. Jackson, you gonna tell me what happens? Whoa! What happened?
What
happened?
That was crazy. It splashed.
It did. Let's try the little one. That's cool. Different, but still cool. Okay, so there were definitely bigger splashes with the larger, low frequency,
Daddy,
bigger
I need
vibrations.
The little one. I need.
Whew, okay, they're gone now. Oh, that was a lot. Okay, so we've touched the ear and the nose. The vibrations, they're so rapid. It's really ticklish, or really tickly. So that's a pretty strong observation. And you also are going to feel that it's just tapping you a lot. The small one, you don't really feel it as much. Probably because it's not moving very far. Right? Remember this one, when we hit it, it vibrated, and you could see that the vibrations were it was blurry. It was really moving far. Okay, so we did the cup of water. To calculate the wavelength, same way we just did, right? Use the numbers. This one again is 261.6 hertz, or 261.6 waves per second. This one's 880 hertz, or 880 waves per second. And then there's some questions to answer down here. Neither of these are going to be none of these are going to be super hard to answer. And we'll talk about them later. As a follow-up to this, I'm going to slow-mo what we did with the cup. Oh, that's right. I almost forgot. So you can do some of this stuff at home with rulers. All right, even though you don't have tuning forks, you can do some of this at home with some rulers. So let's see. So here's a couple rulers that I have. And what you can do, you've probably done this before. You bend down part of it, you hold it near the edge. Done that before? All right, so this is like the longer tuning fork, and then as you bring it back in, hear that? Hear that? How it gets higher pitched. So you can hear that the longer the moving part is, the longer the wavelength is, right? The farther this is moving, longer wavelength. And so that's a higher wavelength, which equates to a lower frequency, right? It takes longer for the waves to occur, and so they're less frequent. And so the pitch is lower out here than it is in here. And you can even see the waves are happening a lot faster here. You can see it, you can hear it. Long wave. Hear that? Pretty cool, right? You can do this with a pencil, but you might break it. Okay, that's it. Check the next video. It's going to be really short. Just slow-moing these.